Hiya, how's it going? In my fourth video, I'm going to be talking about the standard normal distribution, okay? Now, when you've got a normal random variable, x, remember it's normally distributed, mean of mu, and the variance is sigma squared. But of course, with a set of data, the mean does vary. It could be any number. Same with the standard deviation. So what we need to do is we need to standardize it, okay? We need to standardize it. Why do we need to do that again? So we can use those tables. So we can use the tables. And there's two tables, one to find probabilities, and there's another one when you've given a certain probability and you've got to work backwards, okay? But you can't have a table to use when the mean and variance are completely different all the time. So you've got to standardize it. You've got to standardize it. Okay, so when you've got the random variable x, this is what the normal curve looks like, okay? With mean, mu, and then you've got mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, and so on, okay? Now here's the formula we need to standardize this distribution, okay? In order to get to this curve with a mean of 0 and standard deviation of 1, so it goes up 1, 2, 3, we need to apply this formula. It's like a coding formula. Remember coding? You probably had to do that with the mean and standard deviation earlier on, okay? So the standard normal distribution z is given by the formula of x, that is our normal distribution, subtract mu, then divided by sigma. How does that work? Well, look, if we first of all subtract mu from all of the data, then how do we change this? Well, instead of mu there, of course, that would be 0. So that gives us our mean of 0. You see, just by subtracting whatever the mean is. And so then that will be sigma, and then that will be, let's just rewrite this, mu plus 2 sigma, subtract mu, so it's 2 sigma, and then that one there will be 3 sigma. So this one here is going to be negative sigma. This one will be negative 3 sigma and negative 2 sigma. Oops, I put a delta there. I do like deltas because of calculus, obviously. Anyway, there we go. So how do we get it from sigma, 2 sigma, 3 sigma to 1, 2, 3? We just now divide all these by sigma. So if you divide that by sigma, you get 1, 2, 3, negative 1, negative 2, negative 3. Hence, you end up with this standard normal distribution curve, okay? A curve in which we can use the tables in order to work out probabilities. All right. Just another reminder, because I love saying this, okay, to be honest, here's the equation of that curve, okay? So when you're integrating, you're finding the total area under the curve, hence between negative and positive infinity, and then you've got e to the negative half t squared dt, and then you've got this 1 over root 2 pi. It's a lovely looking formula, isn't it? Okay, it's a lovely looking equation, and if you want to know how to integrate that, just look up my video on this. This is my bit of advertising, okay? It's a bit of hardcore mathematics in there, not just calculus, but some polar coordinates as well. It's actually a pretty cool integral. It takes about 30 minutes to go through it. But if you're interested in the actual integral as to why this ends up being 1, then this is a good place to start, okay? Right, so there's a reminder about the standard normal distribution. Now let's do some examples. Okay, so here's an example of how that standard normal distribution works. Suppose we're given x is normally distributed with mean 50 and variance 16. We've got to find probability x is less than 53, and part B, find probability x is greater than or equal to 55. Remember, don't worry about the greater than or equal to, it's effectively the same as greater than, isn't it? So what do we do then? Here's a reminder of the coding that's got to be used, because the tables only work for the standard normalised distribution, which is z. Okay, so first of all, we've got to get it in terms of z. So the thing to do is you put 53 in there. So when it says x is less than 53, it's talking about the variable x. Okay, to get the variable z, you then put x into it. So 53, subtract the mean over sigma. So first of all, we're going to work out what that is. 53, subtract the mean, which is 50, yeah? And then divided by sigma, which is 4, yeah? Remember that is variance, so square root it to find the standard deviation. So that's 4. So 53, so 50 is 3, 3 over 4. And remember, with this work, decimals is the preferred choice, okay? Well, I'm a fractions person myself, of course, but with this work, particularly all the tables, decimals is what you'll be using. So equals 0.75. So this actually, let me just write it here, this is the same as the probability, oh, hang on, sorry, beg pardon, forget I said that. This one, on part A, okay, this one actually is the same as probability that z is less than 0.75, okay? So that's what we're going to work out. Probability that z is less than 0.75, all right? And all we do is just look up our tables and see what that is. Okay, I've written them down in front of me. 0.7734. Okay, so 0.7734. Sorry for the messiness of the presentation. I'm just trying to fit it all in, and I kind of like having that curve there as well. Okay, so in context, of course, we're looking at there's 0.75 there, and you can see the probability up to that point. That's how the tables work. So it's 0.7734. Well, I find it's useful to consider that because you just need to know whether your answer is greater than or less than 0.5. Because up to there, up to 0, it's got to be half, and then from there onwards it's also a half. So 0.7734 sounds about right for something that's up to there. I'm hoping that made sense. Okay. Part B then, just so the board looks a bit better. Can I just put it down over here? So probability x greater than or equal to 55. Good idea to write out the question again before rubbing it out in case I remember incorrectly. So that is part B. So the first thing I'm going to do is to put 55 into there because that's a random variable x. So I'm going to work out what it is in terms of z. So 55, subtract the mean of 50 divided by the standard deviation again of 4. Okay, so that's 5 over 4, 1.25. Yeah, so 1.25. So this actually is the same as the probability that z is greater than or equal to 1.25. I always like to do that first because before you go ahead and use the tables, you've got to know what it is in terms of z. So that's the first thing, and that's easily done by using that formula there. Okay, so probability z is greater than or equal to 1.25. Let's just highlight that in the diagram, shall we? So there's roughly 1.25. We need to work out that bit there. Remember how the tables work though? The tables works, it gives you a probability up to that point. So when we use the tables for 1.25, it's going to give us a probability up to that point, isn't it? Okay. Again, I've got it written down in front of me. That is 0.8944. So that's that bit there, 0.8944 using the tables. Remember, pause the video and just check that you are getting the same readings as me. Okay, hopefully you are. Again, what I say, the diagram is useful because it enables me to put into context what that figure there means. Obviously, it's the larger bit, isn't it? We need to work out that bit there. So in terms of my working, I need to do 1 subtract that value, 0.8944, and that gives me 0.1056, which again sounds reasonable for that bit there. Okay, I'm hoping that made sense to you. If not, just replay it. Alright, so next example then. So you've got y. Well, that's interesting, isn't it? A different letter. It doesn't always have to be x, of course. So y is normally distributed with mean 20 and variance 9. Okay. Find b such that the probability of y is greater than b is equal to this, 0.0485. Okay. Well, the first thing to do really is just to work out what it'd be in terms of z. So let's just do that. So when we have b, that's instead of x, of course. The formula still works for y. So you've got z equals y minus mu over sigma. So you have b, but we don't know what that is, so keep it in there. B, subtract the mean, which is 20, all over the standard deviation, which is 3. Remember, that's the variance, 3. And that's not really helpful at the moment, is it? But that's going to be useful. So I'm just going to rewrite the question. So we're going to find the probability such that z is greater than this, is 0.0485. Okay. I probably didn't make sense there, so I'll just say it again. We want to find b such that the probability of z being greater than this is that. So that's how you reword the question in this case. Okay, that's how you get the z in it. All right. Now, in terms of using the tables, of course, that's not in the tables, is it? Because the tables begin at 0.5, okay, and go up to 1. So what do? Well, just for the moment, consider this on the diagram. So I'm going to put it there. I've got a bit of hindsight, by the way. I know what the answer is, so in case you're wondering how do I know it's there, just because I've looked ahead. Okay. Basically, this here that I'm pointing to, that's the 0.485. Okay, remember, its probability z is greater than. So probability something is greater than that is 0.0485. What we want, of course, is this bit here, which of course would be the difference between that and 1. So that's going to be 0.9515. Okay. So what we can do is we can turn this around and say probability Z is less than whatever this happens to be, okay, is equal to 0.9515. And now we can use the tables to work out what that is. Okay? So when you use the tables, you're not using the percentage points table here, you're looking at the first table, the large one. So try and find 0.9515. Okay, again, I've looked it up, it's 1.66. Okay, so the way you do this is when you're, what's the best language to use here? When you're removing the brackets, I suppose, when you're undoing this, when you found what that is in reverse, it's 1.66, you're effectively removing the brackets. And you've got this, b minus 20 over 3. So that figure there, you see, like I said, I've kind of looked ahead, excuse me. Sorry, that was getting a bit noisy. I've looked ahead and I kind of saw that as 1.66. That's how I knew to draw the line there, you see. What we're saying is that the probability that Z is less than 1.66 is that, okay? And we want to find out what B is, so that means B minus 20 over 3 equals 1.66. So here's where I just need to the calculator. So 1.66, so we're going to multiply by 3, and that gives us 4.98. Yeah, and then we're going to add on 20. I don't need a calculator for that, but there you go, started, so I'll finish. So B equals 24.98. Okay, 24.98. Okay, well, I'm hoping that made sense to you. Okay, this is my last example in this video. I've actually taken this example from a textbook, but it was just so wordy, I didn't want to write it all up. So I've kind of summarised on the board. I'll read it out to you. So it's related to the real world, this one. So it says the blood pressure of an adult population, S. Now they've used S, I hope you don't mind, I've used X. Okay, so the blood pressure of an adult population, X, is modelled by a normal distribution with mean 127, standard deviation 16. So I've summarised that as X, normal distributed, mean and variance. Okay. A medical researcher wants to study adults with blood pressures higher than the 95th percentile. Find the minimum blood pressure for an adult included in the study. So I've summarised that as we need to find the minimum value of X such that it is higher than the 95th percentile. So how do we do that? So what does it mean, 95th percentile? It means up to 95%. So if we're looking at higher than the 95th percentile, we're looking at the top 5%. Okay, we're looking at the top 5%. And that means the probability of being in that top 5%, of course, is 5%. That's what this means, okay? As a decimal, that probability is 0.05. All right, so that's our starting point. So I'm going to rewrite this as the probability of Z is greater than, we don't know what that is, we've got to find it, something, is equal to 0.05. And that's how you phrase this question from a real world context into a mathematical question that you can go ahead and solve, okay? These questions are quite common when you want to find something in the top 5% or top 10% or top 2.5% or top 1%. And the points table is really helpful for these, okay? So the ones they give in the points table, they're set up nicely so you can work out things like the top 10% or the top 5%, okay? So if you use the points table on 0.05, working backwards, that should give you this figure here. And I've done that, I've looked ahead, let me just read off what it says. 1.6449, okay? 1.6449. Maybe just pause the video and check that you agree with me there. So what I'm saying is, we've got our value of Z, okay, such that the probability of Z is greater than this, is in the top 5%. And if it wasn't for X there, that would answer our question, okay? But of course, we've got to find what X is. So the value of Z is that, okay? So we've got Z, which is this, is equal to X minus mu over sigma. So it must be the case that 1.6449 is equal to X. Remember, small case x when it's a particular value, okay, in that distribution. X subtract the mean, which is 127, over sigma, which is 16. Okay, and we just need to work out what X is. Use a calculator for that. So 1.6449 multiplied by 16, and then add on 127. So it gives me 153.3184, okay? Bear in mind this is a real world context. I'm just going to round that to 1 decimal place. Okay, there we go. So in answer to our question, we're looking at blood pressures of 153.3. Okay, that will solve it. Well, I'm hoping you found that useful. I'm hoping that you found the whole video helpful to you. Okay, best thing to do is just practice on your own, particularly using the tables. Okay, it is a skill. It's something that you've got to learn. It's something you've got to pick up. So practice as many questions. Okay. All right, thanks for watching, and I'll see you again. Distribution. Now, why again do we need that? Well, this is what a standard. Well, this is what a normal. Now, if x is a normal distribution, x is a normal distribution. Okay. Now, if you remember, x can be a normal. Why I can't get this? There it is. Now, when you've got a normal distributed, God. So here it is. Z is normally distributed with a mean of 0 and standard deviation of 1. Variance of 1 as well, of course, and it gives us this curve. Now, why is that important again? Because when we've got a standard normal variable, why is that important? Well, when you've got a standard normal distribution, Hi, how's it going? I've forgotten it already. Why can't I remember this? Normal, random variable. Normal, random variable. Normal, random variable.